Welcome to the third part of Lesson 13, where we're going to continue our exploration of normal stress differences and of their effect on the flow of viscoelastic materials. In the last part of this lesson, we discussed how to measure the first and second normal stress difference using rotational rheometry. What we will do now is examine how two viscoelastic flow effects, the Weissenberg effect and extrudate swell, can be thought of in terms of the first normal stress difference. Whilst we can gain an intuitive understanding of both of these effects from consideration of the first normal stress difference, we will see that actually life is a little bit more complicated and that the second normal stress difference is involved as well. However, a useful mental model can be gained by thinking of them in terms of the first normal stress difference, and that leads to an intuitive understanding. So we're going to explore and develop that, whilst also mention the fact that the second normal stress difference is important. So now we know that two normal stress differences exist. We have N1, our first normal stress difference, which is tau11 minus tau22, the one direction being the flow direction, the two direction being the flow gradient direction. We also know that we've got a material property psi1, the normal stress coefficient, the first normal stress coefficient, and that's N1 over gamma dot squared. And we can write similar expressions for N2 and psi2 as well. So we know that normal stress differences and normal stress coefficients are material properties and that we can measure them. We know that N1 measurements are, relatively speaking, quite straightforward in a cone and plate tool, and that we've also discussed the fact that N2 is a challenging measurement to take because N2 is typically a lot smaller than N1 and it's hard to isolate from N1 unless you've got some pretty specialist equipment. So what we want to try and do now is to think about how N1 and N2 affect flows. We're going to, in this part of this lesson, focus more on N1, and in the final part of this lesson, focus on N2. So let's think about an effect that we saw right at the start of this course. When we started this course, the first thing I did, or one of the first things I did, was to show you some videos of some viscoelastic flow effects. And one of the more spectacular ones is rod climbing, or the Weissenberg effect. Let me just remind you what it looks like. Here on the board is a picture of one of my kitchen measuring jugs, and in this measuring jug I've put a solution of wood glue. In the wood glue I have dipped a piece of M10 studding that's attached to a power drill, and I've turned the power drill on and I'm rotating that piece of studding at several thousand RPM. What we can see, as highlighted in this blue square here, is that wood glue starts to climb up that piece of studding. Wood glue is polymeric, it's typically polyvinyl acetate, and it exhibits normal stress effects. So can we understand this phenomenon of rod climbing using normal stress difference considerations? And the answer is yes, we can, and we've already put a lot of these building blocks in place. Let's think of the first part of this lesson and one of the things that we discussed. We discussed the Queller effect, and what that was, if we recall, was you had a cylindrical vat of fluid, in the base of which you had a turntable, and when that turntable was rotated, you found that the fluid bulged in the middle. And we explained this by saying that as that fluid rotates, you have streamlines. Those streamlines are in the angular direction. And we get a first normal stress difference set up, which manifests as tension in those streamlines. And much in the same way that surface tension acting on a bubble results with a higher bubble pressure than the outside surroundings, what we find here is that these flow streamlines, these tensile streamlines, end up forcing the fluid into the middle of this rotational geometry, and we call this the Queller effect, or flow strangulation. So if we have a rod dipping into the middle of this rotational fluid, we can perhaps imagine the net result is that fluid is going to climb up that rod when the rod is rotating. And we find that if we measure that height, we can see that that height is related to the first normal stress difference and the second normal stress difference as well, just to add a little bit of complication to the picture. But there's a very, very nice paper that was published in Soft Matter last year, 2023, by a research team out of UBC in Vancouver, And they revisited this whole problem of the Weissenberg effect and posed it as a rheometric analysis, which is really nice, i.e. using measurements of the Weissenberg effect they were able to isolate N2 from N1. The expression that they found for the rod climbing height involves a few key parameters, and I've highlighted two key parameters there on the blackboard. There's this lumped group of terms beta, and there's a non-dimensional group, the bond number. Now, if we look at this lumped group of terms beta hat first, we'll see that it is a combination of my first normal stress coefficient psi1, my second normal stress coefficient psi2. The really nice thing is that the contribution of psi2 to beta is 4 times the contribution of psi1. Now remember that psi2 is typically 10 times lower than psi1. This acts to redress that balance a bit and makes those psi2 contributions far more significant than they otherwise would be, which means that if we can measure delta H, we might be able to get more accurate information out for psi2, hence N2. The other group that I've highlighted is the bond number, and this is a competition between drainage effects under gravity and surface tension effects. And surface tension I've written using that symbol, which is an alternate version of the symbol phi. So there on the board are the equations that describe the height gain due to the Weissenberg effect. And what we can do is we can look what happens to that height gain for differing levels of viscoelasticity. We can start off by saying, well, what happens if there's no viscoelasticity? In this case, my first and second normal stress coefficient are both 0, hence beta hat is 0. Hence the first term in these square brackets drops to 0, and the delta H result becomes negative, which, if we think of a Newtonian fluid, is exactly what we expect. If we have a Newtonian fluid in rotational flow, then it dips in the middle as a vortex is formed. Think of your bath draining, for example. If, however, we start to add in viscoelasticity, we can perhaps see that there's a critical amount of viscoelasticity for where you're neither going to get a dip in the meniscus nor any rod climbing. And that is going to depend on the angular speed and on the bond number and the density of the fluid. So we can see that the Weissenberg effect is actually dependent on both the first normal stress difference and the second normal stress difference. Life's a bit more complicated than this picture of just flow strangulation, but this flow strangulation is a useful mental model to try and intuitively understand what's actually going on. So let's look at a second flow phenomenon, one that is probably a bane to most people in polymer processing, and it's the phenomenon of extrudate swell. That is, you squeeze something out of an extrusion die, the extrusion die is nicely manufactured a certain shape, and the product shape that you get doesn't resemble the die shape because your polymer has distorted as all the stresses relax. So you have to design your dies to take that into account. Let's give a visual reminder of extrudate swell, and here is a picture of a tip of a syringe. I'm squeezing a viscoelastic liquid out of this syringe. It's a solution of polyethylene oxide in isopropyl alcohol and water. And what we can see here is that the ultimate diameter that this fluid stream takes, dE, is larger in diameter than the exit of that syringe, which is diameter d. We can also see that that point of maximum diameter is some way downstream of that syringe exit. So can we understand this phenomenon using considerations of normal stress difference? Let's think about how we might do it. Firstly, we're going to think what would happen in a Newtonian fluid. Let's assume I've got a Newtonian fluid being squeezed out of a syringe. Let's assume I've got a highly viscous Newtonian fluid, and I'm squeezing it slowly, such that my Reynolds number is substantially less than 1. What I find in this situation might be somewhat surprising, because I do get extrudate swell. The reason for that extrudate swell is if we consider the velocity profile in that blue bit, we've got Poiseuille flow, pipe flow. We've got a no-slip boundary condition at the walls, we've got a maximum velocity in the core of the flow. If we think about what's happening in the yellow bit of the flow when that fluid comes into the outside world, there's nothing holding back the flow at the walls anymore. There are no walls. And so your velocity profile rearranges from Poiseuille flow, parabolic flow profile, through to plug flow. And it's that velocity profile rearrangement that can give us swelling up to 13%. The more normal case for a Newtonian fluid is when inertia is involved. And that's the second case I've just put on the board. When inertia is involved, we get that fluid filament contracting somewhat. And again, it can contract up to about 13%, give or take. And that's in the laminar case. As soon as you get turbulence in there, the results are somewhat different. Now, let's sketch alongside these two Newtonian examples what might happen in a viscoelastic fluid. You can get swelling of order hundreds of percent in a viscoelastic fluid. And there's a very nice approximation that was derived by Tanner and co-workers some decades ago that allow us to estimate the level of dye swell or extrudate swell in a cylindrical geometry based on N1, my first normal stress difference, and tau 21. And tau 21 is effectively the wall shear stress in that cylindrical flow. That subscript W after the bracket means at the wall. And if you think back to capillary rheometry, if we know what the volumetric flow rate of the fluid is, and if we know a measure of apparent viscosity and of the pipe radius, we can very easily work out what tau 21 is. So from cone and plate rheometry, we'll get N1. From considerations of volumetric flow and viscosity and apparent viscosity, we can get tau 21, which means we can estimate how much a given viscoelastic material is going to swell given a cylindrical extrudate. And that's a very, very useful rule of thumb to use. So let's see if we can now understand why it swells. And in order to do that, we need to remember that N1 represents streamlines in tension. The size of N1 is usually dependent on the shear rate, on gamma dot. So let's sketch a typical extrusion geometry. It might be my syringe. The base of my syringe is typically conically shaped, or it might be an extrusion die. Let's follow fluid through this geometry, and there's the yellow fluid filling up the geometry, and it's going from a very wide diameter through a contraction zone and out into free space. And now let's think about the levels of shear rate, hence first normal stress difference, in each of these three zones. So in this first zone, I've called it a low shear rate zone. I've got a relatively large diameter, there'll be relatively low flow velocities because I've got a constant volumetric flow rate and it's a large diameter. There'll be some shear stress for sure, but the levels are going to be low. Consequently, the first normal stress difference will be quite small. So there'll be some streamline tension, but not a great deal. Let's think about this second regime. As the diameter shrinks, the fluid's going to accelerate, and also the radius is getting smaller. So we've got two effects there that ramp up the shear rate. Hence, my first normal stress difference will increase. If we think of this as tension along streamlines, imagine a bungee cord. In our low shear rate zone, we've stretched it a little bit. The diameter hasn't really changed that much. In this high shear rate zone, we've really stretched it, and the bungee cord's got a lot thinner as we've elongated it. What's going to happen then when we go into the shear-free zone? Suddenly, gamma dot goes to 0. Well, imagine letting go of your bungee cord from it being elongated and thin to being non-elongated and a lot thicker. And that's the sort of mental model you can use to think about that diameter increase after extrusion due to first normal stress difference. It's the relaxation of that streamline tension that's allowing that diameter of the extrudate to increase. And if we think back to previous lessons, we know that relaxation is not immediate. It happens over a time scale. And depending on the length of that time scale and the speed of extrusion, we may find, as shown on the board in that picture, that the maximum diameter point may occur some way after the die because it takes time for that streamline tension to fully relax, hence for that polymer to fully swell. So let's recap a few key points. We've just looked at two viscoelastic flow phenomena that in a sort of semi-naive way we can relate to N1 to gain some intuitive understanding. Yes, it turns out that N2 also plays a role in these effects, but it's useful to have these mental models to imagine what might happen. We saw that for rod climbing, or the Weissenberg effect, we can measure the height of a material, and the height of the material depends on both psi1 and psi2, the first normal stress coefficient and the second normal stress coefficient, hence N1 and N2, but there was a really nice analytical result that we can use to relate that height rise to the levels of normal stress. If we happen to know what one of those normal stress difference is with relation to shear rate, for example N1 with cone and plate measurements, then we can access N2 measurements from these data. We also looked at extrudate swell, and what we saw is there's a nice approximation due to Tanner that we can use to approximate and estimate the amount of extrudate swell you're going to get in the cylindrical geometry for a given level of first normal stress difference.